Hi all, welcome everybody to this webinar about the impact of DHW temperatures on energy performance. Should be a really interesting topic, and we've got some great members of the industry speaking today. I'm Ryan Harris. I'm a heat network engineer at Fairheat. I'm currently the Joint Technical Officer at CIBSE YPG, which is the Young Engineers Performance Group. Just a shout out before we start to Richard, third from the right on the bottom, and Jen, fifth from the right in the middle, who are helping out in the background for this webinar. As the YPG, we've got a mission to improve the energy performance of buildings and reduce their carbon footprint. We also try to reach out to young professionals, those aspiring to join the industry, and support them in their professional development. And we as well provide a forum for discussion to enable networking opportunities, promote collaboration amongst members. So hopefully we're achieving a couple of those with this event. Other events we usually run would be seminars, building tours and pub quizzes, but obviously with lockdown this year, some of those have been unable to occur, and we're doing a lot more like webinars like this. If you want to know more about us and the events that we'll be running in the future, then you can follow us on LinkedIn and Twitter, as well as on Eventbrite and on the CIBSE website. I'd definitely recommend keeping an eye on those if you're keen to do a building tour. We've had some really, really good visits in the past, and we did have some more in the pipeline before lockdown. So hopefully in the future we can get those running again. Hopefully you've all seen the details on the Eventbrite page and you joined to watch because of how interesting the presentation sounds. I've given them all a read myself, and I can confirm that they are. A quick reminder for what you'll be hearing. First, we'll have Steve, who's a Regional Director at ACOM and a CIBSE SOFI Fellow, who's going to be introducing the importance of DHW temperatures from a public health perspective. Steve will then be followed by Jonathan, Associate Director at Condal and SOFI Chairman, who will be discussing the different considerations when providing DHW via instantaneous or stored systems. And finally, we'll be hearing from Andrew, who's a Senior Mechanical Engineer at Arup and the Chair of the CIBSE DHW Working Group. He'll be talking about the aims of the group and the work they've been doing recently. Before I hand over to Steve, just a quick note that this webinar is being recorded. The video is going to be uploaded to the CIBSE YouTube channel in the next few days, and whilst the slides will be available shortly on the YPG website. So if you want to rewatch it, or you know someone that couldn't make it, then you can find those there. CPD certificates will be sent out to all attendees in the next couple of days, as long as you've signed into Teams with your email address. If you haven't, or because you're signed in as a guest, or you don't receive one, then don't worry, just email us at ypg@cibse.org. Those details will be in the sidebar. I think Richard's already dropped them in, so just for reference. At the end of the presentation, we'll have a Q&A session, which will give priority to the most liked questions. So if you think anything you'd like to ask or hear discussed, then please just add it as a question at any point in the presentations, and like any others that you think you'd like to hear a response from. And that's enough from me now, so I'll leave you in the capable hands of Steve for the first presentation.
Okay, thanks very much, Ryan. I'll just attempt to share my screen. Hopefully that's right. Hopefully everybody can see that main screen there. It's good. Well, I don't know what parts of the country you're dialing in from, but I'm certainly very, very hot today. So hot water is cold water would be good. Anyway, yeah, let's start. So just from a public health engineering perspective, just provide an insight and overview of the public health design issues that we need to consider. Water hygiene in this case is really linked to Legionnaire's disease, scalding risk, what are the safe hot water temperatures, and legislation for hot water temperatures and control within the dwelling. So that will cover the TMV, and I'll explain what they do a little bit later on. So as a public health engineer myself, just sort of give you an overview what we cover: water supply systems, drainage systems, fire protection, fuel gases, medical gases. But in this particular one, the safe design of domestic hot and cold water systems is where we're focusing on. So as I mentioned, Legionnaire's disease, very important aspect from a water hygiene point of view. There's Legionella is found everywhere in the environment. It could well be in your compost heap at home, actually, as well as open water and drinking water systems. So the perfect temperatures for it to multiply actually align quite closely with domestic water temperatures, and particularly for those that are used in bathing and showering. So therefore we have to be very careful that we design both hot and cold water systems so that we avoid any proliferation of those bacteria. You can not usually get Legionnaire's disease from drinking water, and indeed it's actually not tested in any of the water testing regimes from the drinking water inspectorate. I'll come on to that a little bit longer in a little moment. Yeah, so it's not actually harmful to drink water with Legionnaire's disease, and so it can often be found in drinking water systems. But the important point for us is that we don't design systems that have the potential to allow the Legionella bacteria to proliferate. As I mentioned earlier, there are plumbing outlets such as showers, spray taps, where there's a risk for aeration of the water that could actually enter your lungs. Didn't mention actually, but Legionnaire's disease is a potential to get into the lungs, and it causes a lung related disease. But particularly showers and spray taps, these are provided often with mixed water at between 35 and 47 degrees, and where the aerosols have the potential to enter the lungs. We look at the next slide, which has the growth temperatures for Legionnaire's disease. As you can see, the optimum temperature is around about the mid 30s to 40 degrees, which actually happens to align quite nicely with a showering temperature, generally around about 37 degrees. That also aligns with human body temperature, which is between 36.5, 37.5 degrees. And your lungs are very moist, so obviously if you do get the Legionella bacteria breathed in and into your lungs, then that's obviously where the problem can lie. It gives you pneumonia-like symptoms, and actually the most from data received at highest risk are males over 50. So I'm in that bracket, unfortunately. So those are the death range above 60, and the growth range typically between 20 and 40 degrees degrees C. So as you can see, these temperatures are banded basically to where we want to keep the cold water cold and the hot water hot. And this is the principles of our public health design. We generally try and keep the cold, reduce water storage, keep turnover high, so you limit heat gains to the cold, keep the hot water hot, so consider minimal hot water storage. If you do store it, keep it well insulated, dead legs to a minimum, etc. So there's many documents and legal documents, guidance that we would call upon. The first one I'm going to talk about is the Health and Safety Executives HSG 27274. It provides information on hygienic water systems and water temperature options. Temperature regime, keeping the hot water hot and the cold water cold. However, there may be times when you need to deviate from this, or if you have a building that there may be a risk of lower turnover in the operational period, like a stadia, for example, then you may look at other alternatives such as biocide treatments. So certain systems that we look at for biocides would be chlorine dioxide, copper and silver ionization, chlorine, and stabilized hydrogen peroxide. These are all listed in the HSG 274 Part 2, and there's specific details. The last item, supplementary measures for point of use applications, is something that would be addressed on for healthcare, particularly with specialist areas, or even for reclaimed water, say rainwater harvesting systems, or irrigation systems. Further within that HSG 274, it talks about the temperature regime, as I mentioned, being one of the primary methods that we use to control Legionnaire's disease. It refers to cold water outlets being kept below 20 degrees C, hot water outlets being at least 50, and then it goes on to talk about hot water circulation and storage temperatures. So if you have to store hot water, then you should be storing it a minimum of 60. That goes back to the requirement for the criteria where Legionella bacteria is killed within a reasonable time at 60 or above. And if you have a hot water circulation system, then it's aligning with those temperatures that you can see. Secondary flow minimum 60 and the return coming back above 50. There could be increased temperatures on the cold due to heat gains from ambient temperatures within the building, and the hot water temperature may reduce and fall within the risk of temperatures if it's maybe not well insulated, or there is a dead leg that's introduced into the system. So we try and avoid those things. So the next topic that I'll explain about is the scalding risk. So just to put this into context, if you hold your hand or any part of your body in water that's 70 degrees C, then you'll get serious burns within 1 second. On the other end of the scale, at 50 degrees, it can take 60 seconds or more. This becomes relevant in the building regulations document in a moment. So obviously, the lower temperature, the lower the risk of scalding. So Building Regulations Part G covers the requirements for both preventing excessive temperatures and prevention of scalding. There's a specific requirement to limit the hot water supply temperatures to baths. This is because this has the highest risk with whole body immersion and therefore the longest possible water contact time. As I mentioned before, if you have hot water at 50 degrees, it can take 60 seconds to get serious burns. Hence, if it's 60 degrees, then it would be only 6 seconds. And if you're maybe infirm or well, basically get into a bath that's above that temperature, it's going to take you longer than 6 seconds to get in and out likely, and you're going to have a high risk of getting burns. So also within the guidance, it talks about the use of TMVs to safeguard against the risk of scalding. And there's an information box here, info box 2.3, which actually it relates to healthcare. However, when we're looking at domestic dwellings, we need to consider accessible apartments that could be, homes to the future. So we would consider that to be appropriate to provide TMVs, thermostatic mixing valves, that is to control the temperature on wash hand basins as well, and also on showers. I mentioned thermostatic mixing valves a moment ago. So these control to very tight regimes the temperature. The testing criteria for TMV2 and TMV3 include minimum hot water supply temperatures. It requires a minimum of 52 degrees and a delta T between the hot supply and the mixed temperature, generally between 5 and 10 degrees. So we do have some technical challenges where we're bringing the hot water supply temperature down, which is what will be discussed in further talks later on in the presentations. But there's some technical challenges here with the approvals testing that we need to overcome, particularly if we reduce them below 55 degrees. So supply temperatures, as I mentioned, approved document G states the maximum temperature for bath supply of 48 degrees. It doesn't actually say you have to use a TMV. It considers that as an appropriate method. So it'll be discussed further on, I guess, but with the CIBSE working group, this is something that we're looking at, whether that can be achieved by close control of HIUs or instantaneous units. There's also details within BS 79942 and also a healthcare document, DO8. This covers wash hand basin and showers, baths, in healthcare a lower temperature of 44 and B-days also at 38. So we'd look at this document again, particularly obviously healthcare properties or care homes or anywhere that we may consider there's a higher risk of people in that bracket of risk using those fittings or that dwelling. In addition, the National House Building Council states 55 degrees for sinks. This is also something that's been discussed. I'm well aware of in the CIBSE hot water document, and you can see the table there to the bottom right is the table that comes out of the NHBC document. So the reason for the sink at 55 was for cutlery and crockery washing to get rid of grease, but there's been quite a lot of research that's proving that isn't actually a necessary temperature, and it hopefully can be lowered. And finally, the supply temperatures. So going back to HSG 274 part 2, it states that there's a minimum requirement of 50 degrees to be supplied to the outlets within 1 minute. This is primarily to avoid dead legs and wastage of water by limiting branch pipework lengths, and we would overcome this by using secondary hot water systems or temperature maintenance tape so that we limit those dead legs. The reason also is that it provides user satisfaction, limits the risks of hygiene issues and the wastage of water. So that's my final slide. So thank you very much. I think Q&A at the end, I believe, but thank you. And I'll hand over Jonathan to discuss the comparisons between instantaneous and stored hot water systems.
You're just still muted, Jonathan.
Can you hear me now?
Yeah, all good.
Perfect. It's that famous phrase, can you hear me now? The one that we all use probably daily for the last 3 months. Right, thank you, Steve. That was much appreciated. And so I have now been asked to give you a presentation on the considerations of instantaneous domestic hot water compared to stored water systems. So Ryan kindly introduced us at the beginning, but just to reiterate, I'm Jonathan Gaunt. I'm an Associate Director at Cundall and head up their public health team. I've also had the honour of being the SOFI chairman for the last 2 years and have another 9 months in the position. And I've also been involved with as a member of the CIBSE Domestic Hot Water Working Group. So within this presentation, fine-tuning it slightly, we're going to look at the Legionella constraints for stored water and how best to store it and the energy implications of reducing domestic hot water temperatures in the instantaneous systems. So what are the main goals of this presentation? Well, ultimately, the United Kingdom has targeted to reach net zero carbon by 2050. So that's a tall order which we're all working towards, and we're all striving to better our designs and improve performance of buildings. What we're starting to find is that building fabric and air tightness are improving, and they're going a long way to achieve the requirements. But that's turning a bit of a spotlight on domestic hot water generation, which is now starting to become one of the one of the lead energy requirements, certainly within residential buildings. So ultimately, how can domestic hot water generation be improved to promote net zero carbon? So we need to look at the reduction in generating temperatures of hot water while maintaining water quality. So that is really important that they're done hand in hand. So, as we mentioned, this presentation is going to look at central storage versus instantaneous domestic hot water and what the key issues are. Well, the backdrop of this slide is actually our friend, the Legionella bug, which Steve's already introduced to us. And it's something certainly as pH engineers we are very conscious about, and it's something we strive to avoid, as well as looking at energy reduction. So we talk about instantaneous and central stored hot water. Now, not wanting to teach you all to suck eggs, because I'm sure you're aware of what these systems are, but just as a bit of a recap, instantaneous hot water systems, we tend to typically see within residential schemes, less so within large commercial schemes, and they're typically related to combination boilers and district heating HIU units. And quite frequently, it's a single pipe pass through an electrical heating coil or around a gas-fired burner or something like that, with a single pass from there off to serve the sanitary fittings. So the pros associated with such a system are generally that the units themselves are quite a bit smaller, certainly where you've got heat exchangers, than perhaps a central cylinder. To a certain extent, it's easier to control the water quality because you end up with potentially shorter pipe runs from your heat source to your end fitting, and it's a one pipe system typically. Whereas the cons are, and this is debatable, increased energy required for that instantaneous heating, and that's certainly the case where you're looking to meet that 60 degrees centigrade. You're heating that water instantaneously from 10 degrees to 60 as it passes through that element. So stored unvented hot water. So these you would used to see cylinders, typically vented systems within older properties. You don't see so many properties these days with unvented cylinders, although my apartment does have one. But stored central hot water is typically found within the bigger commercial systems. And it's effectively, the system is a central calorifier, which is fed with cold water. You then have an indirect or direct heating source applied to that source of water, which then elevates the temperature, and that water is then passed out through a circulating return pipe system to all of your sanitary fittings. Now, the whole point of having a circulating return system is that the downstream hot water supply to the building is maintained at suitable temperatures because it is a circulating system. So any heat losses from that pipe are then brought back to the cylinder where the heat source kicks in and then raises the temperature again, which helps control any biological activity in the water. But it also means that you're getting more instantaneous water at your sanitary fittings. So in terms of the pros, the fact that you have a stored volume of water will allow for a certain amount of downtime. If you lose your boiler or power cut or anything like that, then you do have some level of resilience in water supply. It's a tried and tested, reliable approach for thermal disinfection. So if you have designed your system appropriately and your boiler or your electrical immersion heater are sized properly, then you can get the temperatures within those cylinders to suitable levels to make sure that you're actually killing off any bacteria. And then with the circulating return system, depending on where you terminate the circulating branch, you can have pretty much instantaneous hot water at point of use. So we're doing a hotel scheme at the moment where the client has effectively asked for water at a set temperature within 3 seconds of turning on the tap. So you would only get that through really bringing your circulating return right up to your fitting or incorporating trace heating tape or something like that. But as with all systems, it does have cons. It is possible to incorrectly size these units, and you can end up with an awful lot of hot water sat there for extended periods of time doing absolutely nothing. Or equally as bad, you could end up with a system that's been undersized and you end up with people not getting sufficient hot water out of it. What we are finding is that the general ways of sizing these systems, so on the left-hand side of the page here, we've got an extract from the Institute of Plumbing Design Guide, and on the right, we've got CIBSE Guide G. This is guidance set in place to help designers size your central domestic hot water storage, and it gives you anticipated storage volumes per person or per bed space, and an idea of how much you would be expected to store for those sorts of installations, and that covers everything from prisons to residential to hotels to leisure centres. The graph on the right is quite interesting. This one in particular is, I believe, for office space, and this gives you an idea of how much storage you should be providing for litres per person based on a recovery time. Now, typically, you'd normally allow around about an hour for central domestic hot water recovery. But this guidance is actually getting really quite old now. And I'm sure Steve will recognise it when I say that we'll have done a number of surveys around certainly older commercial buildings, and the facilities manager will say we've got 2 vessels and one of them's hardly ever used, and there's just not enough draw off, and that's primarily because some of the guidance actually allows for higher flow rates to fittings and to office spaces where actually there used to be quite nice plush canteens put in place by the management, and there was significant water usage in the catering facilities. What we're finding now is that with sustainable design and with the reduction in water discharge from fittings, there is less demand through the fittings, and so those older schemes and some of the older design approaches are actually starting to become more and more out of date. Having said that, there's been a trend in the last few years pushed by or encouraged by LEED, BREEAM and WELL to actually include more showering facilities for people coming into office space and cycling. And what we're finding actually is that we're seeing now increased peak demands in the morning through people cycling to work. So I suppose the message from this is there's guidance in place to effectively size central stored water, but I believe there's a little bit of a question mark as to how up to date this information is. So in terms of your central storage, Steve's already touched on this, but it's quite poignant to this point in my presentation. And it's about the water regs and HSG 274 Part 2, which Steve's already introduced you to. I'm afraid this presentation's between the 3 of us will bombard you with regulations and temperatures, so just bear with us. The water regs state that hot water should be stored at a temperature of not less than 60 degrees C and distributed at a temperature of not less than 55. It also says, highlighted in red, that this water distribution temperature may not be achievable where hot water is provided by instantaneous or combination boilers. So remember that, because it's quite poignant when we come on in the later section to the instantaneous units. HSG 274, which is a legal document, goes on to state that maintaining a supply temperature of at least 60 degrees C from the heat source and or storage vessel is required, and the hot water circulating loop should be designed to give a return temperature to the calorifier from each loop of 50 degrees C or 55 in healthcare. So with those 2 statements, you will immediately see that there is some discrepancy between some of the legislation that's out there, certainly in this case with the return temperature. And that's partly where the domestic hot water CIBSE working group comes into play, because it's looking at what legislation is in place and challenging it and seeing if it's actually the most applicable. Interestingly enough, HSG 274 then goes on to say, which Steve has mentioned, while temperature is a traditional and a very effective way of treating water, there are other measures that could be taken, and that's including water treatment. So in other words, you don't necessarily have to rely on elevating the stored water to 60 degrees C. There are ways in which you could use chemical treatment to actually treat the water effectively with a lower circulating temperature. And just remember that at this point, we're still talking about stored domestic hot water, not instantaneous. So that brings us on nicely to a very interesting case study. I would love to say that this was one of the jobs that I worked on, but I'm afraid it isn't. But it's a very interesting one, and it's the Great Ormond Street Morgan Stanley Clinical Building. Now, this building actually, I believe, coupled on to some existing infrastructure, and the facilities team at Great Ormond Street were concerned about the condition of that infrastructure. In particular, they couldn't necessarily trace all of the pipework and didn't necessarily know if dead legs existed. So there was real concern with adopting the system and using it for this brand spanking new development. Now, this design effectively looked at reducing the domestic hot water circulation to 42 degrees centigrade. And if you remember back to Steve's presentation about his section on TMVs, this effectively meant that all of the TMVs could be stripped out, which saved on significant cost, but it also meant that Legionella risk assessments were reduced because you have to undertake assessments with dead legs from TMVs where you've got blended supplies at lower temperatures. And so that was a massive positive. But what also became evident was out of 1,598 samples taken between September 2011 and June 2017, there was 100% proof that the pneumophilia control had been adequately managed and that there were no microbiological counts, which is actually really impressive. On top of that, there was a 33% energy saving and a 24% reduction in carbon emissions. So it is a very interesting case study. And some might say that actually, is this the light bulb moment? Is this the answer? Is this what we've been looking for to be able to reduce those central storage temperatures from our 60 degrees C down to something significantly less where we can potentially save energy and do without TMVs? Well, all I can say is that we need to handle this with a lot of care. It sounds fantastic, but there isn't a silver bullet with this scenario. And there's a reason why thermal disinfection has been used all these years. It's because it's extremely effective. But when water treatment is used effectively and correctly, then it's proven that it actually does the job perfectly well. But I think it's important to bear in mind that it relies heavily on a strong maintenance regime. And I think GOSH or Great Ormond Street is a classic example where you've got a very, very good maintenance team who know exactly what legislation stands and what they should be doing in terms of maintenance, making sure that all the chemicals are in place, topped up, monitored. They're doing water treatment regime properly. They're testing and making sure that the counts for Legionella and Pseudomonas are acceptable. So with that care in place, I think there's a very strong possibility that it's a good, reliable and robust scheme. But I'll tell you now, the number of schemes that I've been to have a look round that have been in operation for 2 or 3 years even, where a water treatment system such as, for instance, chlorine dioxide has been left in the corner of the plant room. The FM team don't really know what it's for. They haven't topped up the chemicals and it's been switched off. I've seen that time and time again, and that is absolutely what you cannot afford to do where you are reliant on chemical treatment for controlling water quality in central stored domestic hot water systems. So what happens then when we start incorporating low storage volume heaters? Well, you'll be pleased to know that there is some guidance in place for that as well. We are, as pH engineers, we have an awful lot of guidance in place to make sure that we're designing systems properly and that we're complying to ensure that the public health ultimately is maintained. Now, HSG 274 has a couple of interesting statements here, and it says that low storage volume heaters, which importantly are classed as no greater than 15 litres of hot water in storage, such as instantaneous units and point of use heaters, may generally be regarded as lower risk. And an example of low risk situation is where hot water is fed from instantaneous heaters or low storage volume heaters supplying outlets at 50 degrees C. So we're starting to think about reducing temperature. It also goes on to say that such lower risk systems should be able to achieve a peak temperature of 50 to 60 degrees C and recommended using temperatures less than 50 degrees C only where there is high turnover. Now, you'll be pleased to know that high turnover is very vague and not really qualified in any of the documents. But I think you could probably suggest that residential schemes could be classed as high turnover, and residential schemes are ultimately where we're seeing many of these instantaneous units being promoted. It's at this point where you'll find a lot of public health engineers stand up and say no, because they will be aware of BS 8558 and the water regs and HSG 274. 8558 and 274, I believe, state that the water at the outlet needs to achieve at least 50 degrees C within 60 seconds. And the water regs say 50 degrees C within 30 seconds, although it does state in the water regs that this does not apply where hot water is provided by instantaneous or combination heaters. At the moment, we believe that there's no requirement for either the temperature at the tap or delivery time at the tap set within these documents specifically for instantaneous systems. Now, for those of you who are eagle-eyed, and Steve touched on this earlier, you'll see further discrepancies between regulations and legislation. In the 8558 talks about 60-second rule, and the water regs talks about 30-second rule. So that's a good start. The reason behind that primarily is that water regs are concentrating on water conservation, and they don't want people running taps for ages waiting for the hot water to come through. So they talk about the 30-second rule, whereas HSG 274 and 8558 tend to concentrate more perhaps on the Legionella side, where they believe there's a little bit more flex within the timing. So just thinking about that delivery time and temperature, if we start looking at reducing the instantaneous domestic hot water temperature to say 50 degrees C at the point of use, or point of source, then what sort of temperatures would we be looking at the tap? Well, an exercise has been done, and based on 5 litres per minute tap with a 10-metre stretch of pipe work between the generation point and the outlet, for a 15 diameter supply pipe, which is fairly common for residential, by the time it gets to the tap, that water's dropped to 49.8 degrees C, and it's only taken 17 seconds to purge that length of pipe. And going up to the worst case scenario of 28 diameter, and you don't see many residential schemes with larger than 28 diameter supply pipes. Again, that pipe is purged within 65 seconds, but you're still achieving the 49.7 degrees C at the outlet. So actually, even though we're talking about instantaneous and there aren't necessarily fixed rules associated with that as there might be with central domestic, we're not far off complying with those requirements. So other benefits associated with potentially reducing the supply temperature on instantaneous to say 50 is that it then starts to unlock heat pump technology. So I'm guessing some of you might have seen schemes that you're working on the office where heat pumps are incorporated for domestic hot water and there's a feed into calorifiers, and we're then reliant on immersion heaters to then up that temperature to 60 degrees C to pasteurize the water. Well, by reducing the temperature, then it starts to unlock that heat pump technology and it becomes much more efficient. Again, by reducing the temperature to say 50 degrees C, and I stress we are still talking about instantaneous here, there's potential to reduce the heat emitted from the pipework as well, which has got to be a good thing. Ultimately, it reduces the overheating and potential discomfort to the residents and reduces system energy consumption and also reduces the heating cost for the residents ultimately. But something else that we're seeing as becoming more and more of an issue with PH systems is that we're seeing cold water supplies to premises actually rising above 20 degrees C, so actually entering the Legionella growth band from the opposite direction to the hot. Whereas hot is dropping, we're seeing the cold rising, and this is being exacerbated by the fact that sealing of buildings is becoming so much better, and we're finding hot boxes within sealing voids, which is being exacerbated by LTHW and domestic hot water pipework. Just as an example, this table here gives you an indication of if we were providing 55 degrees C at the domestic hot water incoming supply into the building. If that was dropped to 50, then we're actually seeing a 10% decrease in annual heating requirements just through that 5-degree drop within the incoming hot water supply. If you then compare that to domestic hot water cylinders, as a standing loss comparison, if you say had a 305 litre calorifier which was stood at 65 degrees C, then you'd be looking at 900 kilowatt hours per annum just through standing losses alone. Now, I suppose you could say that's a little bit deceiving because not many premises have 305 litre cylinders for domestic. That's merging perhaps more on commercial, but it gives you some sort of a feel for what sort of losses you'd be looking at. So further benefits are obviously a reduction in limescale. So I think quite an interesting fact is that there's more than 10% increase in solubility of calcium carbonate when water temperature is reduced from 55 to 50. So by dropping that temperature at source to 50 degrees C, you're getting energy reduction, but you're also getting reduction in the formation of limescale as well. And that formation of limescale will reduce on the buildup of pipe walls and will ultimately reduce in maintenance, plant replacement, and will improve the energy performance because that heat can effectively be moved around and it's not being blocked by the limescale. So conscious that I'm wittering on, we're nearly at the end now. In terms of instantaneous hot water, what we then need to really start be thinking about as designers if we are potentially looking at reducing source temperatures to 50 degrees C. Well, simultaneous use reduces water temperature. So if we're generating temperature, if the generating temperature is reduced, hot water flow rate must increase, and therefore if pipework's undersized, flow restrictions will occur and performance is reduced. So we need to think about the pipework sizing, and it needs to be sized correctly to ensure that the reduced temperatures don't have an adverse effect on the performance of any of the sanitary fittings relying on them. It's also really key to remember that we're talking about reduced temperature and the impact with that reduced temperature on potential bacterial growth. So the recommendations that we're talking about here and that will be incorporated within the CIBSE Domestic Hot Water Group guidance is that in terms of reducing temperature, it doesn't apply to systems with vulnerable users. So prime one, care homes or sheltered accommodation, for instance. It's expected that risk assessments should be done within these premises before thinking that you can automatically reduce temperatures down to 50 degrees C within instantaneous systems. So what does best practice look like? Well, this little sketch actually comes out of the guidance that CIBSE are looking to promote. And again, it's for instantaneous units only, but it shows domestic hot water generated at 50 degrees C, and it's exploring the option of stating that we have a benchmark of 45 degrees C at the outlet. Now, what you've seen so far is that with the instances we've been looking at, we're achieving a lot higher than that. But we're looking at pushing the boundaries, I suppose, and just seeing what implications exist. So that is my section. I believe we'll do questions at the end. So I'm now going to hand you over to Andrew McKay, who's going to wrap up. Thanks, Andrew.
Hi, everybody. I'm Andrew McKay. I work for Arup as a senior mechanical engineer, and in my separate role, I'm chairing the CIBSE Domestic Hot Water Working Group. So I'm going to tell you a little bit about what we've been doing and how we're hoping to move the industry on a little bit. So bear with me, right? So we are.
Andrew, we're still on Jonathan's slides.
Are we?
So
Sorry.
if you just pop your screen on Teams.
Thank you very much. Hopefully better.
Yeah, there we go.
Great, thank you very much. Right, so yes, so we are the Domestic Hot Water Working Group is a group within CIBSE that's a collaboration between several like-minded practitioners. So people from SOFIs, people from the CIBSE Homes for the Future Group, and the Domestic Building Services Panel, who recognised that there was an issue in the clarity of hot water guidance and differences in how it's being applied, and particularly due to the changes in technology and culture, I suppose, in terms of how we use hot water over the last 20 years. So we've got together and we're trying to change that, but we want to very much affirm that public health is very much the primary driver, and as it should be for all hot water systems. And we're initially looking at the residential market, as this is the market probably that's seen the most amount of change. As we've moved to heat networks, we've started introducing domestic heat pump technology, and we're seeing the use of heat interface units as we're phasing out the gas boiler over the next few years. It's also quite an important market to look at, as it's generally driven by mass building. So whereas larger building types generally will have a domestic hot water system that's dedicated and designed specifically to their needs with their own risk assessments, generally residential is very much a rollout of the tried and tested. So and as we're building a huge amount of housing in this country at the moment, up to 200,000 or 300,000 houses a year over the next 5 years, it's very important that we start to get that paint by numbers design solution right. So this has been touched on a little bit by Jonathan and Steve, but there is a huge amount of different legislation out there that relates to domestic hot water, whether that's the temperature that it needs to be for to reduce the risk of Legionella growth, or whether that's the temperature it needs to be to avoid burns, or whether that's just a water consumption legislation. And it's coming from many different angles. It's coming from people like the HSE, it's coming from the water board, and it's also coming from NHBC, who we see as a real key driver. So they're a provider of homes insurance, who establish what if they're going to insure a home, they set out the standards that home needs to meet, and so they're essentially protecting the user. And we see them as the guide of what is most practical and useful as an actual hot water temperature for you to use for bathing, for washing, and for cleaning your dishes. So we've seen all of this guidance, and we've said, okay, there's a lot of it out there. It doesn't really all line up, as Jonathan already mentioned, and generally it doesn't really relate to what the market is at the moment, which is for residential, it's very much instantaneous hot water via HIUs. So we've seen that there's these challenges, and we've also noted that there is very little guidance out there that relates to the energy performance of hot water systems. So this is the Future Home Standard that was released last year, and is supposed to be a very forward-thinking aspirational document for how we build homes in the future, both for happy and healthy homeowners and occupiers, but also setting out aspirational targets for how we achieve net zero as a country by 2050. And these are the only 3 mentions of hot water energy efficiency. So adding more insulation to your storage cylinder, potentially considering wastewater heat recovery, and maybe using a heat pump that's got a COP of slightly more than 2. And we thought that really that's not very aspirational, and still isn't really related to how we think homes will be built over the next 30 years. So talking about that next 30 years, this is the context of what we're up against. So looking up there in the top left, this is what we spent as a country. The UK spent its energy on in 2018. So a lot of it was spent on transport, but a good 30% of our energy was spent in the home. And of that 30% of the energy in the UK, 60% of that was on natural gas, so for heating and for hot water. And obviously in a net zero environment, that's got to change. And as a country that's building in the number of homes that we need to build to overcome the housing crisis, and the fact that we're phasing out gas boilers in homes by 2025, we've got to do a little bit better. So I take you on to the second graph at the bottom. This is talking about, this is probably something as energy engineers you're very aware of, but we're trying to, as a country, bring down the amount of energy that we're spending on the electrical grid, because we need to make sure that our grid in 2050 has got enough capacity to deal with enough capacity as a sustainable renewable energy grid to deal with all of our needs. And at the same time as we're trying to bring down the energy that we're spending, we're also adding a lot of energy back in by saying that we need to generate all of our hot water electrically and our heating electrically. So there's a dual challenge there. So we need to make sure that all of the energy that we're now additionally spending on hot water needs to be as efficient as possible. And on the right hand side is again something that Jonathan alluded to, is the importance of hot water now. So this is a refurbishment project that we looked at in Arup, and we looked at by the interventions that we made to facade, to heating efficiencies, we could massively drag down the space heating demand for the property. But actually, unless we do something on the hot water side, there's not really much we can do about that. We can bring down flow rates, but in reality, we still need to generate water hot enough for people to shower and wash their dishes. So it becomes, hot water does become the primary driver for the energy consumption in the home. So this is what we're trying to do. So clarify and unify. So we have all of these dozens of standards that conflict, and we've been through all of these with a fine-tooth comb and pulled out the key bits. And what we see as the key, most of them kind of inter-refer to each other as well, which is quite challenging when you're kind of trying to find the trace of exactly what the requirements are. And what we establish as the key drivers are what the HSE want us to do for Legionella prevention, and what the NHBC want us to do for hot water use. So we've taken their requirements and established what we think based on that is the best practice. And so we've Jonathan's already mentioned what we think our best practice is. I'm going to go into that in a bit more detail, but we've set that out in the CIBSE guidance note that is going to be published in the next couple of months. So that guidance note will contain a lot of evidence over why we're looking to drive towards a 50-degree generation hot water temperature, but we'll also include references to different standards and why bits of standards are relevant to the instantaneous hot water market. And so we're going to send that out, and we were expecting that to be established as industry practice and therefore inform future standards. So we've already been speaking to NHBC, and they've agreed that 50 degrees is ample for what they think the users of a home need for their washing and dishwashing needs, and so their standards are going to be updated from 2021. And we're also in close collaboration with CIBSE Heat Networks team, who are reissuing CP1, so the Code of Practice for Heat Network Design, and that's going to be released this year and is going to be aligned with the findings of the CIBSE guidance note. So this is again what Jonathan's already touched on, and what we believe is the best practice to maximise energy efficiency and ensure safety in the home, as well as for a Legionella perspective, and as well as reducing the risk of scalding. What we've set out is a very specific scenario that this applies to, which is a block of flats served by a communal heating system, as well as a communal boosted cold water system. Each dwelling flat is served by its own instantaneous heat interface unit, and there is no stored hot water, and only a small volume of water within the pipeway to outlets. And that's a scenario that we've specifically agreed with HSE, but one that we believe is applicable to a huge amount of the residential design that's going on in the UK at the moment, and therefore will allow us to make the biggest impact on the market. And on the right hand side, you'll see the diagram that Jonathan flashed up earlier is what we're recommending. So we want to generate 50-degree hot water at the plate heat exchanger in the heat interface unit, and then we have this second test, which is the 45 degrees C delivered in 45 seconds. So what it's really important to note is that we're not saying that 45 degrees at the kitchen sink is acceptable. What we're saying is this is a test from cold of the performance of the heat interface unit and the pipework leading up to it. So at the moment we have a under Thames Water, for example, in London, the test is 50 degrees from cold within a minute, and we are pushing that to 45 degrees within 45 seconds, which aligns also with how BESA set out heat interface unit tests, which require that the heat interface unit is able to deliver 45 degrees within 15 seconds from cold. So that 45 seconds at the tap includes 15 seconds from the HRU to heat up from cold and 30 seconds to get your hot water out of the tap at the end. And then we actually expect that with a well insulated system, which it would need to be to achieve those times, that temperature will very quickly get to 50 degrees and therefore more than well match what would be acceptable under pretty much all guidance at the moment anyway, even for stored systems. So that is the end of my presentation on where we're trying to get to, and now I think it's time for some questions. Thank you very much.
Yep. Okay. So as I said before, questions are on the side. If you want to add any more now, we are still taking them and continue to like any that you want to hear answered. I'm just going to read them from the most liked downwards. So the first one we've got is, and this has been partially answered by Steve already, but I think we can maybe discuss around that. How often and for how long do you need to maintain 60 degrees when storing hot water? I've seen continuously 1 hour per day and 1 hour per week recommended in guidance documents and by manufacturers. I think, Steve, do you want to read out what you've said in response to that?
Yeah, sorry, I was going ahead with the answering those, so I'd clear the backlog really. But yeah, obviously, if you're storing hot water, you want to keep the temperature up as much as possible because of the fluctuating between the temperatures and the Legionella risk temperatures. So that's what I was getting at there. Really, you design it for a period of recovery period. Generally, we would look at a short recovery period to limit the heat losses from that appliance. But that heat source, primary heat source, is available 24/7. So if you have a preheat, for instance, of a solar thermal system or low-grade heat, then that may be where this question's coming from. We interpret the regulations so that needs to go through a pasteurization cycle once a week. I don't know if there's any other people on the panel here that would agree or disagree with me, but that's
yeah, I'd agree with that, Steve. I think just on that 1 hour per day or 1 hour per week, that might be alluding to the fact that you perhaps boost your central domestic stored water up to say 70 degrees as opposed to 60 to make sure it's getting a full pasteurization cycle. But as a designer, I would always make sure that it's sat at 60 degrees as opposed to just achieving those temperatures perhaps once a day.
Yeah.
Okay, we'll jump on to the next one then. So has there been any development to look at a diversified sizing method for hot water storage in offices, similar to that of BSEN 806 on residential? I think that may be most relevant to Jonathan's presentation, but if someone else has something there.
Yeah, I might be shot down in flames at the moment, but I'm not aware that there is. The guidance that is in place, I suppose take a step back. There's quite a lot of spotlight on legislation at the moment in terms of some of the water systems, because if you look at European codes and other international codes, there's a strong argument to say that many of our pipe systems are actually oversized. And when you look at the sort of our resultant pipe sizes through the calculation processes that we undertake in the UK, we often come up with a larger pipe size that some of the other brothers and sisters in the international community use. I think this trickles on through to your question about sizing for domestic hot water as well, in that I'm not aware of any design that's under review at the moment to change that design process. I don't know if the other guys are aware of anything, but at the moment we tend to fall back onto the CIBSE guidance and the IOP guidance, but then we also use engineering best judgment, certainly where we're looking at banks of shower facilities for sports centres and office changing facilities and things like that. So for instances like that, then we would put our engineering hat on, and with the experience that we have, come up with a robust design in that way. So we don't necessarily always lean on historical documentation.
I would just add to that, Jonathan. I think you're specifically talking about pipework sizing there, and I'm not sure if the question was related to pipework sizing or the storage.
No, well, the storage as well, to be honest. But I don't think I'm not aware of anything in terms of the storage that's really being reviewed at the moment. But yeah, I mean, same with pipe sizing, with the storage sizing, we would take an engineering approach on some instances to understand how much water is called for in terms of domestic hot water for peak shower usage and things like that, and fine tune the storage requirements to suit. So I wouldn't say that any engineer or few engineers blindly just follow legislation and the design guidance. I think as the very nature as engineers, we like to question, and I think it's fair to say that many engineers, certainly ones that I've met, still question that guidance. It takes an awful long time to change guidance that's set in place and design standards that are set in place. And I think if there's any criticism, it's trying to keep abreast and update those standards and guidance in a timely manner to actually move with the times.
Cool. We'll jump on the next one again. So this question from Alistair saying, do you use BSEN 806.2 to size systems these days? And I think, Steve, you've made a start on this one as well. So if you want to jump in there.
Okay, yeah. So CIBSE Sophie did some research and actually published a technical document on this a couple of years ago, well, 2016 actually. So BSEN 806 has some restrictions when you're talking about above 12 litres a second. It doesn't cater for those systems above that size. So and also it's limited on the engineering information, particularly on velocities in that document. So residential, yes, we would say definitely applicable for residential within each apartment. If you can, for instance, if you have a fairly small to medium sized residential development, then you can use that throughout. But for commercial or very large schemes, then you'd be looking at 8558 or IOP guide, because it gives you, as Jonathan mentioned earlier, it gives you much more information really with regard to the tables that are available to consider a sensible engineering approach.
I would just add to that, Steve, the CP1 update this year is recommending the use of DS439 for district heating systems sized for hot water. So that gives an approach for sizing, integrated approach for sizing for hot water and for heating, and it does give a lower total diverse flow rate than 806. And that's based on a series of studies that the CP1 development team have been undertaking over the last couple of years.
Yeah, okay, that's good.
Cool. So next one we've got is other European countries, notably Denmark, only mandate a 45°C at the outlet in residential. Do you think that we'll see guidance move towards 45 degrees in the near future? I think probably a good one for you, Andrew, and the DHW group.
So I think as I can't remember, Steve or Jonathan mentioned just now, it's extremely slow to move legislation forward. So in terms of what we've done in the Domestic Hot Water Working Group is that we've seen the opportunity to align existing legislation, which and interpret existing legislation, which very much is bottomed out at 50 degrees. If we wanted to go to 45, if we thought that 45 was safe, which is a question that we would need to consider in great detail, then we would need to change legislation, which is quite a hard thing to do. So in terms of the short-term gain, we've looked at maintaining and aligning current legislation. It's worth noting that there are significant differences in culture between the UK and Denmark. So things aren't always as concrete as they seem. We have a difference in how we use hot water, how hot water systems are sized, and they use much more manifold approach to hot water in residential. We don't tend to use in the UK. So there is subtlety, which means that we can't just pick something up from one country and use it here. But that said, there would be lots of benefits to moving to 45. I think one of the other questions mentions the use of TMVs and whether we can reduce the use of TMVs in residential. That problem would go away. 45 is almost a completely safe temperature, but it's a big step, and I think it would need to take a considerable amount of research before we proved that we were happy with that in the UK.
Okay, next one we have here is have TMV manufacturers been involved in the conversations about dropping DHW temperature to 50 degrees? Typically, TMVs need at least 55 degrees on hot feed, between 5 to 10 Kelvin difference between upstream and downstream sides to operate properly. I think I have seen quite a lot of TMVs where you can actually do less than a 5 to 10 degree drop, but I'll let you guys step in if anyone wants to jump in on that.
I can do this one. So we've spoken to, so we've looked at the market in detail at TMVs, and there are TMVs that give us a 5 degree approach temperature, which would allow 50 degrees temperature to be generated and 45 degree bath temperature to be achieved. It's worth noting that the NHBC requirements for bath temperatures actually only require from an instantaneous unit to deliver, I think, 41 off the top of my head, or maybe even 40. So there's an opportunity to use a TMV. So but basically what we see this is giving you the flexibility to choose a TMV if you want to use a TMV with a wider approach. So I mean, really it is the 5 degree is at the top end of the market, because essentially they're paid for testing that shows that it works at that level. For a TMV to be sold in the UK, it just needs to meet the BSEN regulations, which only stipulates a 10 degree test. So any TMV that's available that's chosen to test at a higher level than that is going to be by nature more expensive. So if you wanted to use a more expensive TMV, you give yourself a greater range of opportunity of hot water temperatures. But if you wanted, as a designer or a specifier, to use a TMV that was, say, 10 degrees, you would either have to accept that you had a 40 degree bath temperature, or you'd have to push up your hot water temperature on the other side. But the guidance that we're pushing towards the 50 degree gives you the flexibility to move between those ranges depending on the equipment that you want to use. From an energy efficiency perspective, I'm very much a believer that the market should be moving towards a 5 degree approach temperature. There's no technical reason why that's not achievable, and most manufacturers say that actually it is achievable. It's just not been tested and isn't guaranteed.
Okay. Next one we've got here is, I believe this is in reference to the discussed updates to residential regulations. It says, do you expect similar changes to be brought in for commercial settings and public buildings? I don't know if someone wants to jump in on that one.
I don't know, to be honest. I've not seen or heard of anything in the wings.
I think what you talked about, Jonathan, your the chemical treatment, I think a wider spread acknowledgement of the energy efficiency benefits of lowering hot water temperature and the importance of it will lead to more use of that type of system rather than a thermal thermal disinfection.
Yeah, good point. Potentially so. Yeah, I mean that certainly sort of opens the floodgates, doesn't it?
But in terms of, I think in terms of regulation, most non-residential do involve elements of storage, and therefore will require some element of disinfection. So the requirements for that aren't going to change. You are going to need to kill your Legionella somehow. So whether that's thermal or chemical. I don't see a significant change in the market there, but there is all the other bits that we alluded to in terms of reducing your storage, reducing your pipe work, working around, I think somebody mentions it here, working around the grid, so matching the heat up times to when the grid is best suited to operate efficiently. All these kind of things I think are going to be much more important in the commercial sector over the next few years.
Another one we've got here on commercial, I think this is addressing kind of a follow-up question to the discussion on stored water and pasteurization cycles, saying with commercial environments where these buildings have intermittent occupancy, during holiday and shutdown periods, can the timed operation of those storage tanks be off with a daily or weekly pasteurization cycle, potentially to 70 degrees for an hour? Do you want to touch on that, either Jonathan or Steve?
Potentially yes, but you would need to make sure that when that system comes back online, you've had full pasteurization of the whole system, and it's really important to achieve that. Personally, you know, for weekend outage with commercial schemes, I would keep the system in play and keep it circulating, because you know that you're getting that full water treatment. But I suppose if you're talking potentially about schools that are shut down for extended periods of time, then there may be the potential to then sort of step that system down and make sure that it's fully commissioned sort of before everybody comes back at the start of term to reuse that building. I don't know if you have a different view on that, Steve, or as a sort of a designer, whether that would be sort of the approach that you would typically.
No, exactly the same thing. Yeah.
Okay.
It's the issue is that you're you know, you would have to stop the circulation system, so therefore you're getting the hot water temperatures dropping and the risk of those temperatures falling into risk issues. And then how do you bring that whole system back up to pasteurization? It's very challenging. Yeah, it's not something that we would really recommend. However, you know, where you have an alternative to temperature regime, you know, biocide treatment, then these things are possible. We've got schemes where we were concerned about the cold water system demands on high-end resi, because you don't know about the occupancy. We've got biocide treatment, chlorine dioxide, as a secondary system. And that was because we were concerned about the cold water becoming too hot. Now what we're talking about in the forum here is bringing and the cold water is getting too hot because there's too many internal gains, partly because of the primary hot water distribution, because you're keeping the HIUs fully charged up to delivering 55 or 60. Now we're looking at keeping a biocide treatment in because we're lowering the hot water temperature. So it sort of turned it on its head, really. So yeah, there's a way to get around these things.
I think linked in with that, Steve, I think that's a really good point. But every building should have a Legionella risk assessment as well, which should clearly lay out your maintenance processes, whether you're shutting down the systems for short-term periods, and what you need to do when you then reintroduce those systems, and also to identify perhaps points, water supply points in the building that are irregularly used, to make sure that they're properly flushed through and that you get circulation through the system. And even now, I still see buildings where the facilities manager just looks vaguely at you when you ask to see that document. So, you know, while there's legislation in place and there are risk assessments in place to help people try and save energy by decommissioning systems and then bring them back online and everything else. I still have concerns that the general knowledge within the industry, certainly with those that are operating and running these buildings, isn't necessarily quite up to par. And that's a very, very sweeping general statement, but I think it's so important with water systems that those who are maintaining and operating them understand what they need to do and are complying with their specific Legionella risk assessment for their building.
Okay, so we've got two I think you've already addressed here. So next one says, what about radiated heat losses and increased energy consumption on stored water systems? I think you may have touched on this in your presentation after they asked the question, Jonathan.
Right.
Is there anything you'd like to add?
No, not really. I mean, it's, you know, it's just, yeah, if you've got a tank of hot water, no matter how good your insulation is going to be, you're still going to ultimately end up losing some heat out of it. And one of the things that we've found, certainly from what Steve alluded to, no matter how good your insulation is, you can have a system such as a cold water supply pipe routing through a sealing void next to LTHW and domestic hot water. You can have the best insulation on that in the world, but over a period of time when water's stagnant and that cold water sat there, it will ultimately end up reaching its surrounding temperature. So yes, if you've got hot water cylinders there, it doesn't matter how good your insulation is, you'll still have energy losses from it, and that varies between manufacturers.
I could just add to your numbers on the heat losses were interesting, Jonathan, and those CP1 numbers that I think it's around about 500 to 600 kilowatt hours per year per dwelling. That number is related to all of the pipework from the tap all the way back to the district heating plant. So it's quite an aspirational target that the district heating systems are going to be driven to try and achieve. So there's a lot of heat loss that happens in that stagnant time that needs to be insulated and looked after. And if you throw any kind of storage into that, just looking at the numbers that Jonathan put up, that 900 kilowatt hours, that puts a really big dent in it, whether that's 900 for 300 litres or 450 for, say, a 150 litre tank. That, I mean, it's already too much. So instantaneous units are really where the district heating network is wanting to go.
I won't name the manufacturer.
Okay, next one here is another where Steve, you've made a start on is improved building fabric performance also creating a risk that cold water in buildings is getting warmer? And if so, how is this usually managed?
Yes, it is creating problems. I can think of two schemes off the top of my head. One in which they were selling penthouses for 120 million, where they were getting 32 degrees centigrade water out of the cold tap. And another one, student resi, where they were having significant heat gain issues with the cold water supply, and it was to do with, and I'll just qualify that, I didn't do the design on it, and my company didn't do the design on it. We were asked to come and have a look at it, but so no pack drill or anything. Yeah, what we were finding was that pipework was being routed through ceiling void hot boxes, certainly in high-end resi, where the architect, the last thing he wants to see is an access panel or a shadow gap or anything like that, where you've got any potential air movement through those ceiling voids. You've got pipework passing through next to domestic hot water pipework, lighting, ballast, everything else. And with low usage in high-end apartments, the water sits there and it heats up. But we're also seeing it with the increase in performance of air tightness of the buildings, and it comes down to the sort of the natural ventilation discussion of buildings as well, and allowing for some air movement, because we are finding that the services are heating up. And in terms of mitigating against that, Steve touched on it earlier, talking about chemical dosing to try and provide some sort of gatekeeper approach to try and condition the water, but also we've seen circulating return systems on the cold supplies as well, actually, which have come back via chilled water heat exchangers to try and control those temperatures. And those have only been brought online where the temperatures on the cold water supply are, you know, getting up to sort of 16, 17 degrees, where you're approaching the limit of what's acceptable, which would be 20. Although, you know, if you try brushing your teeth with 20-degree water, it's not particularly nice. So yes, it's an issue, and there are a few ways of skinning the cat. You know, there's the one with circulating return, there's chemical treatment, but yeah, they are being considered, and I'm seeing them used more and more.
Obviously, there's a safety first approach with making sure that you've got a way to know that your cold water is the correct temperature, it isn't a Legionella risk, but I think there's a lot that we can do at designers at an early stage in terms of passive design to reduce that. So to reduce that heat gain happening. So Jonathan mentioned things like shadow gaps, but just things like separating out your risers, putting your cold water plant room not in the same place as your hot water circulating pumps, things like this that you need to get right in the building design. Need to be thinking about it all the way, because there will be a problem at the end if you don't, and you'll either end up chilling your water or dumping your cold water, and neither of which is a particularly good outcome.
Yeah, just on that, Andrew, that's a good point. There are manufacturers out there that promote, I don't think they call it water dumping, because that would be a bit too crude for them, but it's a way in which they monitor water temperature, and if it reaches a certain level, they will discharge it to drain or potentially to a harvested water source. And I think you just have to be careful with approaches like that, because some water authorities will see that as wastage of water and non-compliance with the water regs, even though ultimately you're trying to address a Legionella issue. But also, even with dumping that water to a harvested scheme that perhaps might be used for WC flushing, even with WC flushing, you still get aerated water. So you're effectively discharging warm water where you know you've got Legionella issues into a harvested system, which is ultimately aerating that water again, which doesn't really help anybody. So while those schemes are available, I think you've just got to, it's horses for courses, and you've just got to go into those design decisions even with open eyes.
Next one we've got here is quite a blue sky one, so anyone who'd like to talk about it can take it. It says, has anyone got any opinions on emerging ambient loop systems? Zeroth and our thermostyle systems employ a two-stage heat pump generation process, but minimizing hot water temperature can really boost COP. Thoughts on what to expect in the future, and which direction do you think the industry is going?
Do I? So I do have some thoughts. Ambient heat loops, I think, in terms of an overall system efficiency, can give you some excellent numbers. I have two concerns, I suppose, with how they're coming into the industry at the moment. So one of which is there's an interpretation of the energy regulations that say that ambient loops don't need to be metered, because the heat is being generated by the heat pump that sits within the apartment, which essentially means that the freeholder, the landlord, the energy services company is under pretty much zero obligation to provide anything other than what they might or might not put into a leasehold agreement. And that's quite a dangerous road to be on, because that means that they can operate their equipment as they want to do and pass all of the cost of lower efficiencies onto the tenant, which might not be the overall system efficiency that we thought was really, really great when we were designing it and selling it to our clients. So that there's a danger there, and from a cost perspective to the tenant, and also an overall efficiency perspective. And I think also my other concern is that I think if you were a mass house builder, it's quite an appealing, and you were just going to run a very simple energy centre, it's quite an appealing system, because you can buy an air source heat pump that's going to run quite efficiently, not a a smaller proportion of the hot water that you need, and that's it. You don't need any more equipment other than the HIUs in the apartment, and then all of the rest of the capital cost of and the cost of the maintenance goes on to the person who lives in the apartment. So when they buy the apartment, they adopt the heat pump that lives there. And honestly, I've got enough problems in my apartment with a tap not working properly. I don't want a 4-pipe heat pump in my apartment. If I'm going to have to maintain it and look after it and pay a service agreement. So I think from a mass house builder perspective, it's great because you just move all those problems to somebody else, and it's a bit rubbish from a tenant. I think if you spoke to somebody like a social housing provider or somebody who did build to rent, they would have very different views over it, because the amount of maintenance as a whole that needs to be done on, say, 200 heat pumps instead of maybe 2 heat pumps obviously is much bigger, and potentially there's a big difference in embodied carbon as well. But there are obviously excellent global efficiency increases to be had, and if the system is well run and commissioned exactly as it's designed, I think it's got good potential. These are my opinions in 2 minutes.
I think that was very eloquent. I haven't got much more to add to that, I'm afraid to say.
Yeah, covered that well. Okay, I'll jump on to the next one. For commercial offices, would proposed point-of-use water heaters for toilet cores and centralised system for showers be more energy efficient than a centralised hot water system for the entire building? And is there any advice on when to propose which system?
I have to say that's the approach that we typically take for office buildings. Central storage for the showers, and and local electric. I haven't got a lot of science behind it, but that's the approach we normally take, and we feel it's a pretty robust approach.
I think we've I would agree. We've also been thinking a little bit about body carbon on this one, and we're potentially an area of concern. And to be honest, we don't know the answer. But a point-of-use water heater, there's a big difference in the market between a high-spec point-of-use water heater and something you can buy for a tenner, and something that you buy for a tenner which might be what actually ends up being installed, has a expected life of maybe only 3 or 4 years, which means that there's a lot of replacement, which wouldn't necessarily be the case with a centralized system. So it's just something to think about. And I'm not saying, I think generally I'm still of the view that the point of use is the way to go, because of the amount of hot water losses that you have in a centralized hot water system as you're taking hot water up and down risers.
I think we've got not very many left here. So one more is more of a commercial question. Is there an approved guidance for showering within office applications, as in people showering versus total occupants? I believe that's relating to kind of a commercial usage diversity. Is there any of those that you guys know of?
Not that I'm aware of, but we normally allow for around about 10% of the total office population cycling in at the moment, just as a general rule of thumb. And that's feedback that I've had from manufacturers as well in terms of their specification of hot water cylinders, and we haven't had any problems with it, but I couldn't hang my hat on a document that says that. That's where the engineering judgment comes in.
Yeah, that's also been backed up on where we're looking at reclaimed water systems for grey water as well, isn't it?
Yep.
So the sort of 10% seems to work at the moment. Yeah.
Sorry, I'd just seen the question above. I don't know if you just skipped over it, Ryan, but I thought it was quite poignant. Somebody's asked the question: water can legally be supplied by the water undertaker above 20 degrees C. That's absolutely correct, and that's the problem that we're facing. And we have our own legislation that we need to address within the building. and yet I was involved with a scheme down in Stratford, where the city authority mains was routed very close to the district heating mains, both of which were shallower than they should have been, and the water coming into the building during the peak summer months was about 25 degrees C. So whoever's made that comment, you've got a very good point, and it's absolutely correct, and it emphasises the problems that we have as designers trying to design suitable systems in the building.
And we've had something very similar actually on a healthcare project, where obviously, you know, it's absolutely paramount. The cold water is cold, and yeah, so you've got a non-compliance before you even start.
Yeah,
so you have to chill it.
Yeah, we are running out here, but I think one more I can do is, could you kindly suggest the degree of effects of avoiding stagnant flow pipelines in design and introducing time-controlled evacuation valves that may help with Legionnaire protection? I can't quite follow that one, but if someone can, then...
Well, the time-controlled evacuation valves, I think, was is touching on what I mentioned earlier about the sort of the dumping of water if it gets to a certain temperature or it's been sat there long enough, and I think you have to be very careful with that. And if you are looking at using such a scheme, then I would really recommend having dialogue with your water shippers before you go too far down the line. I think there are other ways to approach it, such as having loop supplies. I didn't quite get the first bit of that question, I have to admit.
No, I'm not sure about that either.
Okay.
If the person who's wrote that's still there, if you want to quickly drop in a clarification while we address one more, then we can answer that. I think the last one here that's a question is, have you looked at the use of thermal stores for instantaneous water heating, where energy can be stored, e.g. cheap rate green electricity, to store water at 80 degrees and then drawn off instantaneously? This reduces the electrical load of the instantaneous water heater.
So acting as sort of a preheat store, presumably. I mean, if it sounds very similar to what we would have done with solar thermal, to be honest. So you use your solar thermal effectively as a giant battery, and you have larger volumes of water to store that energy while you can harvest it, and then act as potentially as a preheat to reduce the overall energy at any one time, to raise that temperature up to a suitable level. So I think it's sort of coming from the same direction, and I think, yeah, I mean, it's certainly got legs to look at for sure.
That thermal preheat is on the primary side as well, so that's got a lot of advantages. You're not storing water at lower temperatures. Yeah, that's something we've looked at and progressing. Yeah.
From the perspective of the hot water working group, we've talked about that sort of system, but we've been very much thinking about what we focusing on the mass market, and and the mass market is the HRU, for the fact that it's lean and small. So systems like that could offer greater efficiencies and should be considered. I think we should be looking at all opportunities for energy efficiency and good hot water delivery. But in terms of what we've been looking at so far, it's not the example that we've been focusing on.
Cool. Well, I don't think we've seen a clarification on that previous question, so I think that's all the questions done. So unless anyone's got any other quick closing remarks they want to make, I'll wrap this up. I think. Anything anyone wants to add on the end? No? Cool.
No.
Well, thank you very much to Steve, Jonathan, and Andrew for speaking and answering all these questions, and thanks everyone for attending.
Thank you.
Thanks very much for listening.
Yep.
Thank you.
Thank you.